Excellent. All right. So for the focus of today's lecture is how to extend all the techniques that we've learned so far to the situation where we cannot fully describe our system in terms of states and actions. Okay? Possibly because the state space or the state action space combined is so large that it requires some compression to be made about the structure of the state space. Okay. This is one possibility. Or another possibility is that we have partial observability of some limited form of our system, in the sense that we do not have access directly to states, but we have access to something which is a corrupted version of the state. So the combination of these two problems, partial observability or just the enormity of the size of the state action space, are good enough reasons to resort to function approximation. And as a matter of fact, in most problems of interest, you have to use function approximation. We will come with examples shortly. So the key messages for today will be of two kinds. So the first message will be showing you how you can do effectively function approximation when it is theoretically safe to do that, when there might be troubles arising, and why. Okay, so the lecture ends with several words of caution about wildly using function approximations and the possible pitfalls that you may encounter. Okay, but let's start first with the simple stuff. So as we did earlier, we're going to break down the lecture in two parts. So in the first part will be just about using function approximation to learn approximate values of a policy. Okay, so first the learning step, and then we combine learning and control, just like we did for the tabular case. Okay, the tabular case means the situation where you have matrices and vectors. Here we want to deal with situations where you have more complex representations of the state value functions other than just matrices. This is clearly a situation in which you are very much interested in. For instance, if you do robotics, in robotics, degrees of freedom are continuous. So potentially there's no way whatsoever to write down a matrix. Okay, you cannot write down a matrix of positions, a matrix of angles without doing some approximation. And this is one of the kind of approximation that we are dealing with now. Okay, so in function approximation, let's start with the first step. So the first step will be predicting the value of a policy. So yeah, maybe just 1 second before I go there. I just have to sort of maybe recap a bit where we are in our diagram, so you sort of make sense of all the path that we've been doing so far. So allow me for a brief general recap. So you might remember that we've been working with this diagram in which we've been sort of categorizing our problems in terms of our knowledge of the model. And our observability. Okay. So, and here we have the best situation that you can possibly have, the one of Markov decision processes, in which there are, for instance, finite states and actions. And then we know that by solving, by means of dynamic programming, the Bellman's equation, we can obtain optimal policies given that particular model. And then we've been discussing what happens here in the middle. If you want to find out a proper extension of Markov decision processes to the realm of partial observability, then you have to combine the Bellman's equation with some notion of inference. And one possibility is to use Bayesian inference. And if you combine that, you end up with partial observability, partially observable Markov decision process. You might remember that here in the gray area here in between, so it's something tries to address the problem of decision making when the features, so when the state space is not entirely accessible. We also discussed approximate dynamic programming. That is a way to solve the Markov decision process, that is to solve the Bellman's equation by using a more compact representation of the value function. For instance, a linear approximation of the value function. The way that the reason why I'm insisting on that is because we will sort of be doing something similar to that now, but in the realm of temporal difference methods. So from this side of the graph, then we moved up here when we discussed temporal difference learning, both for prediction, that is to compute the value of a function without a model, and for control, such as SARSA and Q-learning as typical examples, or expected SARSA as well, etc. Okay, so now we would like to make a step finally to this area here, where all the interesting problems lie, in which you have limited or no knowledge of the model and limited observability. And of course, one way to go there is to sort of try to use the concepts that we already been introducing here, and I will repeat today, to the realm of temporal difference learning. So we want to go in this direction using a function approximation. So what is the idea? Well, the idea is that in situations where the state space, just to fix the idea, situation where the state space is very large, it often happens that you have a very limited set of examples. So your trajectories in state space will cover just a limited number of states and possibly of actions. So you would like to do something which is very typical in data science, that you would like to extrapolate from these examples, that is to generalize from this set of examples to find out policies, decision makings, value functions that extend well beyond the set of examples that you will be able to visit. Okay. So, and clearly here, reinforcement learning joins forces with other parts of machine learning. So there will be all the devices that come also from supervised learning for generalization. Will be useful in this context. Okay, so this is the part of the reinforcement learning which makes closer contact with the more classical approaches of machine learning. But remember, here the goal is not to classify or to discover structure, but remember always that the underlying goal is optimizing some objective in terms of long-term rewards. Okay. So this is where we will be moving, in this area we'll be moving for today and also for tomorrow, but with different approaches than today. Okay, so what does it mean in practice? So in practice, the idea is that we want to move from a description of our value function. Okay, so we are, I have to revert to the previous specification. So first we want to learn the value of a policy with function approximation. This will be the first part of our lecture. And the first thing that we want to do is basically we want to replace our value function which is a vector. And the state space, we assume that is very large. So for instance, suppose that this is grid world with an extremely fine resolution. So you want to describe a grid world over a world which is, I don't know, 10 meter by 10 meter. So a large room, and with a resolution of 1 millimeter. Okay. So this makes for an enormous amount of states. And therefore, you might say, okay, do I really need that resolution? And even if you consider 1 meter, this still is an approximation because space is not discrete, it's continuous. So what if I want to represent the movement of my robot, moving robot, my vacuum cleaner machine in this big room or in an apartment of the size, without recurring to having a big table which describes every point with the resolution of 1 millimeter. I should be able to do that, right? And how do I do it? So the goal is basically to replace this full tabular description. So this is a tabular description with some approximated form, which we write in this formal expression. Okay, so this is the value for each state, but now this is described by a vector of parameters or weights. We can call them weights. And these weights belong to some, say, d-dimensional space, where the dimension of these weights we would like to be, for instance, much smaller than the dimensions of the state space. So this is a low-dimensional description of our value function. And of course, for this approximation to be successful, there must be some structure in the problem, of course. So if your problem is extremely dependent on this on the state, so if for every state something very different happens, this approximation is doomed to fail. Okay, but if there is some underlying structure, such as the problem can be described with a lower number of degrees of freedom, then this approximation can be successful. Example in robotics. Okay, so think about a robotic arm. Robotic arm has many degrees of freedom, just like our arm. So for instance, our fingers have lots of degrees of freedom. And then there's the wrist, then there's the elbow and the shoulder, okay? So each of these degrees of freedom has an angle, okay? So the space of configurations for my arm is extremely large. It's already very large dimension. But suppose that I have to take a hammer and hit a nail. Do I use all these degrees of freedom? Well, actually, this kind of movement is extremely low dimensional because maybe I just control 2 angles, maybe. Okay. So if I have to train my robot to hammer a nail, I don't need the full set of degrees of freedom, right? I just need a lower dimensional subspace. So it's very unlikely that your optimal solution will require your fingers to do like this every time that you nail the hammer, you hammer the nail, right? So conversely, if you want to teach your robotic arm to play a piano, you will need to describe many more degrees of freedom. So your description should be complex, but certainly you don't need all of them, right? Because there's no point in playing a piano this way, right? So if there is some structure, might be simple or might be complex in your problem, then there is opportunity for compressing your description. How good an approximation is and how to do it, that's, of course, the interesting part of the question, which might be problem dependent, okay? Very good. So this is the general setting. We would like to map our problem of learning, the tabular version, so the full vector which represents the value of our function, into some lower dimensional representation. And of course, this expression that I'm writing here is very general. Okay, so this contemplates every possible parameterization of my value function. But in practice, there are two main architectures for this, which we will discuss. So the architectures for approximation. So in general, you can have linear approximation, which means that you are writing your value function as a product. Let me use the same notation as in Sutton and Bartow, so you don't get confused if you read the chapter. I think he uses X for the features, yes. We're going to describe this as a sum over the weights times some xi's. Okay, so another way of writing this is W, which is a row vector of length d times the column vector x, again of dimension d, for every s. Okay, so that's the same. So this is a linear approximation. What does that mean? Well, it means that suppose that here I have my high dimensional space of states. Okay, so this is the coordinate for the value in state 1. This is the coordinate for the value in state 2. This is the coordinate for the value in state 3. And then there are many, many other dimensions which I'm not able to draw, of course. What this linear approximation is doing is that, in fact, it's trying to represent every. So suppose that my value of a policy is a vector here. This is the true value of the policy. And then what this approximation is doing is that it's actually using a linear subspace. Okay, so all v pi of w are vectors which lie in this subspace, whereas the true value is somewhere here. Maybe you are on the good subspace, so your true value for that policy is lying in that plane, or maybe you're not, okay? But nevertheless, the idea of linear approximation is that you're just cutting out a lower dimensional vectorial subspace of the possible value functions, and you want to find the parameters which represent better your value function here. Okay? So the intuition here is quite straightforward about what the goal would be. And then there is a second architecture, which of course is the opposite of what is linear. But this is in practice, this is a way to non-descriptive characterization of the possible descriptions that you might adopt for your parameterization of the value function. In some particular problems, you might have specific ideas about how to model your value function. So you might choose some specific class of nonlinear functions of the parameters w. But more in general, there's no particular reason to choose a priori one specific nonlinear expression. So what you typically do, even though it's not necessary, is to use some universal approximator. So what is a universal approximator? Is a class of functions, okay, which are able to describe any possible function within a certain class as close as possible, okay? So you have a certain class of functions which depend on the parameters, and the idea is that you can always choose some parameters in order to get sufficiently close to your target function that you want to describe. So all this seems very, very abstract, but in practice, what people use as universal approximators are artificial neural networks. And in particular, feed-forward ones. Okay, so you see we are narrowing down our set of possible nonlinear function approximators. So we start from a broad class of whatever is nonlinear, then we restrict to artificial neural networks because they have these properties of being able to approximate, and in particular to feed-forward networks which have that property. And in fact, we can even narrow that down to a simple situation. So the simplest case is a situation where you just have one hidden layer. I am assuming that you have some qualitative understanding of what I'm talking about when I talk about feed-forward neural networks. Is anyone totally in the dark? My dear diploma students, have you been discussing this already with someone? I guess so. No? First time ever that you hear artificial neural network?
Yes.
Very well, so to speak. Okay. So very, very superficial. I mean, you will be discovering this very, very soon in the classes you're taking on machine learning. Okay, I'm talking to the diploma students now. But anyone else from the other side of the world, you should probably already be exposed to this, right? Okay, good. So I will try to compromise and not to spend too much time. But the basic idea is that you can construct a nonlinear function approximation in the following way. Suppose that you have an input, okay, which is some vector r which belongs to some space with dimension m, and then you can feed this input into a certain set of objects which we call nodes, maybe one component per node, for instance. And then there is some operation which transfers this input to a second layer of nodes. Now I will tell you what these nodes are in a way that is something like this. So this is one possible way to do this. Okay, so on and so forth. And don't let me draw everything, otherwise it becomes a mess. So what do I mean by graphically describing this object? That there are some operations that are done here which convert this input into some output in each of these nodes. Okay, for instance, one common choice is to take the input across all these input nodes, which each component of this node takes, each node takes one component. Then you make a linear combination, okay, which is sort of like a linear matrix here times the initial vector, and then you take a nonlinear transformation. So what this graphical description means is that we are doing two operations in sequence. First, we collect these inputs, these components, and we combine them somehow according to some weight matrix, which makes a linear combination. And then we make a nonlinear transformation, which typically has the form of a sigmoidal function, but not necessarily. It's a growing function. You just have to satisfy very mild conditions on this nonlinear transformation, which is called also the transfer function. And then after that, you collect all your information back again into a set of nodes. Okay, and here maybe you just do a linear collection. Okay, so then you just sum up everything with some linear operation, and then you have in output some vector y which belongs to Rn. So this seems like a contrived construction, but it's sort of the mathematical abstraction of what a real network of neurons would do. That is, to collect information from every neuron, make some sort of nonlinear filtering operation, and then send these signals to other neurons. Only that in this case, you see that there is the distinctive nature of this mapping. So this is a function. Okay, this is a function f which maps x into y and depends on the weights, that is, on all these parameters that are inside the function. And this is called the feed forward because the flow of operations goes only in one direction. So once neurons have received information and passed it on, they do not see it again. So why do we care about such a specific construction of a nonlinear approximator? Because it's possible to prove mathematically. And this is what Cybenko, I don't remember the year off the top of my head, but Cybenko proved that even such a simple construction with only an input layer here, an output layer, and a hidden layer, this is enough to approximate arbitrarily close any given function which goes from n to n under technical conditions of boundedness and whatever. Okay, but for any practical purposes, you can use this as a universal approximator at the price of having a very large hidden layer. Okay, so the number of nodes that appear here in the middle might be very, very large to describe certain kinds of functions. So this is one of the reasons why you often do not use such a simple architecture, even though it's theoretically powerful, but actually you can prove that you might need an exponentially large number of these nodes in the hidden layer, so an exponentially large number of parameters in order to approximate certain functions arbitrarily close. And these functions are not even very difficult to write down, okay? So certain logical operations, for instance, require a lot of parameters to be described by a neural network like this. So what you can do instead is to add more layers. And if you have a structure which is composed by one input, one output, and several layers in the middle, which are connected in this one directional way, feed forward, then you have what is conventionally called a deep network, or deep, shallow, depends on the number of hidden layers that you have. But for reasons that are partly understood and partly yet to discover, these neural networks, which are very deep, have a much intuitively, I mean, we can make a point about how they work, but technically there are some still some wrinkles to be to be smoothed out, but they have the power of approximating functions with less parameters than what a shallow network would do. Okay, so they have a larger expressivity. Doesn't matter. The basic message for us is not the connection to neuroscience, not the connection to visual, to computer vision or to vision neuroscience. Is the fact that there is a class of nonlinear functions which are pretty natural choices for our nonlinear architecture of the approximator. So that, not surprisingly, they have been used intensively to solve problems in reinforcement learning using nonlinear approximation. Okay, so this is what is the outline of the possible approaches. What we want to do now is to discuss in detail what would happen if we try to learn an approximate value of a function, like we go back to this question here, in absence of a model. So we want to combine this notion of function approximation with the temporal difference methods, okay, and see whether we can apply our stochastic approximation ideas to the situation where we have function approximation. So in order to do so, what we want to do here is to take a little step at a time. And we are going to introduce one quantity that is our objective for prediction. Okay, so let's go back to this picture I drew here. So this plane here is what you have in a case of linear approximation. Okay, so the linear approximation is just trying to approximate this with the plane, and in the nonlinear situation, which is here, there is a more complex manifold that you expect to be describing. Okay, so this is my depiction of something which is curved and depends on the parameters. But again, you have to reason in very high dimensions, so this is not very accurate as a graphical description. And of course, these W's, these weights are, so to speak, the coordinates on these manifolds. So over a plane or over this surface, the green surface that I drew. Oh, sorry. So in a nutshell, what we want to do is basically to find over these surfaces the points which are closest to my true value function. Okay, so we want to move over these surfaces and find out which are the points which are in some sense closest to the true value function. So we have to define a sort of notion of a distance from the true value function. And this is what the prediction objective does. So this prediction objective, which now I am borrowing the notation of Sutton and Bartow for lack of any better choice. So Sutton and Bartow call it value error. Not that I like very much this notation, but let's not introduce different names for things that have already been used. So this is a measure of how far my approximation is from true value function. So it should contain my true value function for that policy that I'm trying to evaluate. Okay, the policy here is fixed. Remember, we're not trying to control anything for the moment. This has to be taken minus the approximation. Okay, squared. So this is for each state how far my approximation is from the true value for that state, given a set of parameters. But of course, this is not enough. I have to find a way to sum up over all possible states. And how do I do it? Okay, so I have to weight different states differently. And the most natural way to do it is to weight each state depending on how frequently you visit that state according to that policy. Okay, so if you have a policy, your process will jump around over states and it will spend some time on each state. Okay, so this is a natural way of weighting these differences, these square differences. And you might remember that we have introduced this object eta of s, which of course depends on pi. And this eta is nothing but the number of times that I visited the state accounting for discount. Okay, so an explicit definition is defined as sum t going from 0 to infinity, and then I have gamma to the t, and then the probability of being in state S at time t, so that let's write this properly. That the state of my system is actually S at time t. Okay, and this of course also depends on the initial distribution of states, which I'm not writing. Okay, so you pick a state according to your initial distribution, and then you follow one trajectory, and every time you step on a state, you keep a counter, and you discount with your gamma. Or, as you know, you can also kill the process at every step with the probability 1 minus gamma, which is an equivalent way of obtaining this sum. So this is a quantity which we have already introduced earlier on, and this defines our objective for prediction. It's very important to use this particular quantity because it connects with what happens on trajectories. If you use a weight function here, so this is a sort of average time, average number of visits. Under policy pi. If you choose something which is very different from that, you might end up with bad estimates. Okay, so this is important that this has to be the so-called on policy. It's called the on policy. But for now, let's just accept that this is a meaningful description, and let's see what happens if we try to minimize this quantity. Okay, so we're going to do something which is quite intuitive, and that is we want to make some gradient descent in the space of these parameters. And if we take the gradient of the value function of the value error, how does it look like? So the gradient, let's call it gradient. So this is the derivative with respect to some coordinate w, gradient of the value error. Well, I just have to go through this simple math. Perhaps I had a definition. Oh, yes, that's fine. It doesn't really matter. It's going to be 2 times sum over s of pi of s Notice that the policy is fixed, so it doesn't depend on the choice of the parameters W. The only part which depends on the parameters W is this term here. So this is just going to give me B pi S minus B hat S W times the gradient and carry up to minus times the gradient of the approximation. Okay, so I just applied a trivial derivative operation. And then the key step here is that, remember, I cannot use this gradient directly because I don't have a model. And so I don't know this, and I don't know this. So the gradient is not measurable if I just have this sequence of states that I'm visiting. I have to replace this object with something which I can measure. So we're going to do this in two steps. So first, we're going to take care of this. And now here you see where it comes in handy, the fact that this eta pi is the number of visits, because I can immediately replace this quantity with -2, the expectation along the trajectories generated by the policy of V pi at the state t minus the approximation at the state t, the parameters, times everything is under the expectation, times the gradient v of the state st. So this is the real reason why we chose that particular weight function, because it allows us to express that gradient in terms of an expectation of another quantity. So this means in practice that we can construct an unbiased estimator of the gradient of the error, which is -2 times this. Okay, so we have a value error and we want to minimize it. So the idea would be, okay, why don't we take gradient descent? If we take gradient descent, we will be approaching some local minimum. Whether it's global or not, it depends on the kind of approximation we're using. Okay, so this is one thing that we always have to keep in the back of our minds. If we do gradient descent, we can get to a local minimum at best. In some situations, like in linear approximation, this would turn out to be also global minimum. But in general, could not be the case. So for instance, if you use a neural network, you might as well find yourself trapped into a local minimum rather than in the global minimum. Okay, so always careful about this. So we have made the first step in that direction. So now we can estimate our gradient and use stochastic gradient descent to approach that point. But still we have a problem, because what is happening here is that we still have, we still have this quantity here, which we don't know, because that's exactly the quantity we want to estimate. So this is our target object. So this expression, although correct, is useless so far. So how do we do this? So we have, as we also had in the previous examples, we have two possibilities here. Possibility number one, we can do a Monte Carlo. So we are in state ST, and we run our system in the future, and we replace this V pi of ST with the sum of all rewards from, say, T prime, gamma, T prime minus T of the rewards of T prime minus T plus 1. Okay. So that's what Monte Carlo does. You look at your trajectory, you are sitting in state ST, and then you launch, you spawn your future trajectory from that, and you compute the reward, the total cumulative reward discounted, and you use this as an estimate. So you replace your true value with the random estimate. This is good because this quantity here, okay, which is your estimate of the target, is unbiased because the expectation of this is exactly the value function. So once you've done this, you have in fact constructed an unbiased estimator of the gradient of the value error. And therefore, you can learn how to optimize the parameters omega. Okay. So this is good, but there are limitations to this. It's expensive, it has a high variance. We discussed exactly the same points when we were discussing Monte Carlo for temporal difference learning. And the situation here is the same. Okay. So you would like to do something better. And this something better is the second option. Better or worse, it depends on the case, but in general, it's better. And it's the point of temporal difference learning. It's called the operation of bootstrapping. You don't know what the target is, so you replace it, replace the target with a new object derived from your approximation. So what is it in this case? So you have an approximation of your value function in your hands, which corresponds to a certain parameter W. And then you use this to construct your expectation. And the way you do it properly, catch the exact definition, yeah, is that you replace this with the reward that you get plus gamma, your current estimate at the new state minus V. So you see what's happening here. You aim at reaching something, but you don't know what that something is, but still you have an estimate of where it is. So you sort of use your estimate to project it out and bootstrap, that is to leverage on your current knowledge to construct your target function. Of course, by doing this, you introduce bias. Okay, so this is a biased estimator. But typically, it has a lower variance. And therefore, it provides you with a technique in order to approach. So notice that while this approach is a true gradient method, in this approach, we are breaking the structure of the gradient because we are replacing our true gradient with our true prefactor here in front of the gradient, this part here. we are replacing this with some approximation. So this kind of approach is called also a semi-gradient. Okay, so this is just so you encounter, if you encounter the name, this means that we are deforming our estimate of the gradient with using bootstrapping. Fine. In summary, this provides us with an approach to this problem. Sorry, just give me a second. I will connect that later. No. I'm running short of battery, so I have to take a second to connect. Apologies. Okay, that's better. All right. So this sort of leads us to our algorithm, which goes under the name of semi-gradient approximation for value for policy evaluation. So how does that work? So you start with initially you have a policy pi that has to be evaluated. Okay, so as usual, when you have to learn the value of a policy, you set some fixed policy. Then you choose some function, some approximator. Choose one. Linear, non-linear, maybe neural network. Then you have the usual parameters like step size in the learning, etc. So step size alpha, positive. And then you initialize weights. Okay, you start somewhere. If you're linear, it doesn't really matter. If you're non-linear, it might be important. And then you loop over the following set of operations. Start with some S, so pick an S. So let's say initially you pick, so you can have a loop over episodes. Again, you can partition your learning into sequences of episodes in which you make restarts every time. And then you choose initial state S. And then you have a loop over time inside an episode in which you choose an action A according to your policy for that particular state. Having chosen the action, you can take action A and observe the reward and the new state as usual. Okay, so this is a typical interaction you have with your environment, be it robotic or just the code which produces your outcomes according to some hidden generative model. And then you update the weights according to your semi-gradient algorithm, which I just wrote above a few seconds ago. This is the learning step. And then you have the reward plus gamma, your estimate at the new status prime, of weight, minus b. Sorry, I have to rewrite this because it's going to be ugly. So let me split it into two parts. compute the TD error. Let's call it delta equals the reward plus gamma, your estimate at your current value of the state and with your current parameters. And then update W, like W going into alpha, delta, and then you have the gradient of your value. Okay. This is valid for all parameters simultaneously. Then you set your new states into your old state, and then you close the loops. Okay. So this is the inner loop over time, and then there is the outer loop over episodes. And you can repeat this many times until convergence. Okay. Whereas usually your convergence criterion is that, for instance, your gradient is not is becoming small enough, okay, which means that you are approaching some local minimum. So this algorithm provably, but not we don't give the actual proofs, but provably takes you to a local minimum in general. If the approximation is linear, this is also the global minimum. If the approximation is nonlinear, you have to be careful. So as usual, as in a situation where you might have many local minima, a good idea would be to restart from different initial weights choices many times so as to explore the possible opportunities. If you use a neural network, in particular a deep neural network, potentially you are exposed to the fact that there might be local minima, and you might be finding solutions which are not too close to your true value function. But it turns out that with the addition of several tricks, in deep neural network, you can almost always avoid this issue for reasons that are not entirely being clarified so far. But it's one of the sort of magic that happens with deep neural network, that they are able to approximate even though they are in principle prone to several problems like overfitting, and that is finding local minima rather than the global minima. Okay, but this is entirely a different subject for a lecture, so we don't discuss that. Okay, so okay, I think it's a good time to stop here and take a break. And in the second part, we will discuss in detail what happens for linear approximation. And then we move on to discuss the situation where we have control, or maybe we postpone that to tomorrow in order to have time to discuss everything properly. So probably I will go for that second option. So we will discuss more in detail what happens only with the learning the value of a function for today, and we postpone the discussion of control to tomorrow. Okay, so let's now take a break and we reconvene at 10:20. Any questions so far? No. Okay, see you later then. All right, so let's have first a closer look to what these semi-gradient methods look like when we have a linear approximation. So we're going to just look at this, and we just have to replace in these expressions for the temporal difference error and for the update what we have when we explicitly assume that our approximation takes the form, it's linear form, sum over I, wi. So these vectors here are called the features. And as you might remind from our previous picture, they represent basically a basis function in the linear subspace that we want to use to describe our value function. Okay. So it's a linear approximation. That these are vectors xi, and we are taking any linear combination of these vectors to represent our value function. So clearly, this is also, like I wrote before, you can compactly describe this as WT transpose X. So this is the feature vector. These are the components. This is the feature vector. And this is the weight vector. You can think of those as observations. So if there is a state, you can take an observation, which is the value of this feature xi. Okay, it's a observation. So what does the temporal difference error look like? Well, it's the reward that you get. Then you have plus gamma, the value function in the new state for that weight. So it's going to be W transpose X of S prime minus the current value function, which is WT X of S. So it's very easy to construct the temporal difference error. You just have for the current weight to multiply times the feature vector for your current state, multiply times the feature vector for your new state, and then take this combination. Also, because of linearity, it's very easy to write down what is the gradient of the value of the approximation. And this is just the feature vector. Because the value is a linear function, so if you take the gradient along each component, you get exactly the components of the feature vector. So that summarizing, the update is W prime equals W plus alpha, and then you have your temporal difference error, which is explicitly WT X. And this is multiplied times X. Okay, so all these are the visited states. Okay, so being even more precise, I can put time indices. So this is going to come T plus 1, T plus 1. This is S T plus 1. This is ST, and this is ST. So every time that I make a step, I update all the vectors proportionally to their feature. So if the feature is 0 for some state, I will not update it. But if it's not 0, I will update. Now, an important remark is the following, which is not particularly useful from the practical point of view, but it's conceptually very important. So suppose that you have your features, you have D features, and suppose now that that D is exactly equal to the number of states. Okay, so this is not particularly useful because we say that you're using a set of features as large as the states themselves. So there's no obvious advantage in doing that. So all our motivation was to reduce the dimension of the space. So in this case, we are not doing that. And let's suppose that your features are chosen in such a way that xi of S, so the ith component of the feature for state S is 1 if S is equal to A and 0 otherwise. So we have as many features as states, and in practice, the feature identifies one state. So geometrically, what does that mean? It means that in our representation earlier on, of our values as vectors in the space, so where we had some linear subspace like this. Okay, in general. In this case, in particular, in general, the feature vectors were like vectors like this, x1, x2. In this particular case, which we are considering here, there are as many feature vectors as components, and these are just the orthonormal basis of our vector space. So this is a very simple limiting situation. The interesting thing in this case is that if you replace these features inside your update, so what do you get? So now let me work component by component. I get W component I at time t plus 1 from here. I'm just replacing component by component of these vectors. This is W I at time t plus alpha, and then I get RT plus 1 plus gamma. Now, what is this scalar product here? I'm picking only the component of WT, of W, which corresponds of the weight, which corresponds to the state ST plus 1. So this is W component ST plus 1 at time t minus W component ST at t times the feature X of ST, but this is just 1 of I equals ST. I've been just taking the semi-gradient algorithm, and I've been using a specific set of features, which are just the basis vector of my full vector space. Why am I doing that? Because if I do that, I recognize that this iteration rule is exactly TD0 tabular. It's exactly the algorithm that we have been discussing a few lectures ago. I just have to recognize that in this case, my WI are just my values for the state I. So if I replace this, the fact that this is my approximation to the value for state I, this is exactly temporal difference learning 0. So stochastic approximation. So that's where the two ends meet. So you can regard these semi-gradient methods as extensions of temporal difference learning to the case of linear function approximation. Fine, this is interesting because it sort of gives us a safe ground, but the question is how is this useful when we use heavily function approximation? So what if D is actually much less than the number of states, which is the interesting situation for linear approximation. So in this case, there is a result which is due to this, I guess. Let me check the ref. Yeah. So this is a result by Cyclis and Van Roy, 1997, so rather recent. You can prove that by using the semi-gradient method. So semi-gradient method converges to a value of the weights, which we call TD, like temporal difference. Okay, so with linear approximation, if you apply this general rule here, you can prove it's not a particularly difficult proof. It's contained in the Sutton and Bartos book. You can prove that this iteration converges to a fixed point, and we're going to call this fixed point omega TD. Actually, I don't think we need a star if we comply with the notation of Sutton and Bartos. Okay, this converges to this object. And it's useful to compare this with what happens if you find the absolute best approximation. Okay, the absolute best approximation has something like there is a, if you look at the minimum overall possible W of the value ever. So again, geometrically, in the general case, so it's better if we go back to this previous drawing, which is okay up above. So in this linear space, the point which is closest to V pi in the sense of the VE error, okay, which is not exactly the Euclidean distance because it's weighted by the residence times. But this is, in a sense, your optimal, your closest point. Okay, so this W star is the arg mean over W of the VE. Okay, so it's the closest point within a linear approximation to the true value. Temporal difference learning or semi-gradient approximation gets somewhere else in general. Okay? And this is what we call our WTD. So one is interested in knowing what's the difference in performance. So how far off are we from the true value if we use our semi-gradient approach? So it converges, which is good, but it converges to something which is not necessarily the best. And the reason why there is this gap is because temporal difference has a bias. And so this bias does not entirely go away with function approximation. So the relevant result, let's scroll down. Okay. The relevant result is that the actual value, the error that you make, if you converge with your semi-gradient method to a certain value of parameters, is smaller and equal than 1 over 1 minus gamma of this minimum. Okay. So this is both good news and bad news. Okay. So this is good news. So if your linear representation includes the true value function, okay. So if V pi belongs to the space which is spanned by your features. Okay, so if in your lower dimensional representation, your actual value is sitting on that point, this means that the minimum of the value error is 0. Okay, so you can get to the point, to the true point. And therefore, if this is 0, then this implies that TD linear approximation converges to V pi. Okay? So the bad news is that if V pi does not belong to the span, so to the subspace generated by your features, and gamma tends to 1, so you have a very long time horizon, then this bound is not particularly helpful. So this means that there might be situations in which you make a big error. So notice that if you use Monte Carlo methods, that is, if you use true gradient methods, so this is the situation which we have been describing above here in green. If we use an unbiased estimate for the target, that is, we use Monte Carlo. In this case, which is the case we have been picking in green, in this case, your sequence converges to the true W star, which is the argmin. So in this case, Monte Carlo always converges. So here it's a delicate choice between using Monte Carlo with a high variance and a lot of computation and a lot of data, but which probably converges to the optimum, that is the closest point accessible by your approximation, or to introduce bias, have a more effective algorithm, but risking to be far off the actual closest point because of the bias you have introduced. Okay? So there's no clear winner here. It depends on the problem at hand, whether one works better or not. But usually, trying with temporal difference errors with semi-gradient methods is a good way to go. Okay, so we basically have seen that this linear framework is more or less under control. Of course, the big question here is that, but how to construct features? So how do you choose the set of features that are best for your system? So here comes really the interesting part, because it's a little bit of craftsmanship and a little bit of machine learning, in the sense that for some particular problems, especially ones in robotics or the ones in which you have some good understanding of what the physics or the math of the problem is, then you can handpick your features. Okay, you can say, okay, I think those features are good for me for this problem. For instance, in navigation, in grid world, you might have a sense of well, which kind of states can be grouped together in a single state, which is one way of doing function approximation, linear function approximation. Or you might find other intuition in other systems, like in robotics, you sort of have an idea of what are the relevant degrees of freedom for your problem at hand. So this is a part which requires significant a priori knowledge about a problem. Or you can use some other machine learning technique beforehand in order to construct a representation. Okay? So either you use insight or you use machine learning, like, for instance, what is called representation learning, that is unsupervised learning, for instance, in which you sample your system and you try to extract the features before even starting to evaluate the policy. So this is also a possibility. Of course, another way of doing this, which is entirely orthogonal, is to give up all these things altogether, use neural networks, which do not have features, but have no linear description, which are, however, universal. And then you can crank up the machine and try to find the best way by optimizing your weights by using semi-gradient methods. But you have to be careful because, like I said earlier, when you use nonlinear function approximation, there is the risk of making even worse errors if your system overfits. Therefore, you have to find techniques which are available in the literature, like dropout methods and the like, which allow you to mitigate this problem of finding local minima rather than global minima. But this is, of course, we are not at all entering into this subject because it's a subject for itself. I just want to end up with a word of caution and say that if you have substantial a priori knowledge, or if you have data enough to run some supervised learning before in order to find a representation, a linear representation, this is theoretically safe ground. Or you can deploy all the power of artificial neural network, but there you are in uncharted territory, and your algorithms may or may not converge. And this is only for the part which concerns policy evaluation. Tomorrow we will see when we add control, the situation gets even more complex. Okay? So that's, I think that's it for today. Any question? No? Okay. That's not the case. I'll stop the recording.